Hello friends, welcome to my channel Computer Engineering Made Easy, and I am Anilita. Today I am going to show you a super easy way to convert any binary number to their decimal equivalent. Please stay tuned to the end of the video to get a clear picture of the method. So let's get started. The origin of the number system came from the word digits, which means fingers. Since human beings have only 10 fingers, originally we had 10 symbols to represent the number system. The number 10 is also referred to as deci, and hence the name of the number system was referred to as the decimal number system. In the decimal number system, we had the numbers from 0 to 9. But what after that? In order to get the next set of numbers, positional rotational was used. So, the same numbers were repeated once again in the units position. However, since we did not have anything in the tens position, we can consider that we have 0 in those positions. After 0, we have 1. So therefore, we set the value in the tens position as 1 in the next cases. Similarly, in order to get the next set of numbers, we set the value in the tens position as 2. In a similar way, for the next set, the number becomes 3 in the tens position. In this way, we can continue till the number 9 to get the last number as 99. But what after that? Again, we will now look into the hundreds position. See, in the hundreds position, we did not have anything till now. That means we can consider that we have 0 in this position. So after that, that means after 0, we get again 1. So you see, we have repeated the same set of numbers once again, but in the hundredth position, we have now set the value as 1. This is how the numbers continue, and this kind of repetition is what we call the positional rotation. So now let's see how we can actually get the value of a decimal number if we are given the digits in the position of units, tens, hundreds, etc. First, we will make a table as shown here. The positional weights increase linearly from right to left starting from 0 as shown in the first row of the table. In the next row, we have the base value. Now, the base value indicates the number of unique symbols used in the specific numbering system. Since the decimal number system has 10 unique symbols, the base value for the decimal number system is going to be 10. Finally, we list the symbol of each position in the third row. In order to calculate the value of the number, we simply find the cumulative sum of the product of the symbol to the base raised to the power of the positional weight for all positions. That is, we multiply 1 to 10 raised to the power of 3, 5 multiplied to 10 raised to the power of 2, 2 multiplied to 10 raised to the power of 1, and 8 multiplied to 10 raised to the power of 0. Finally, we find the sum of all of them and we get 1528 base 10, which is the decimal value of the number. Now that we are comfortable with the decimal number system, we will take a look at another numbering system which is used in the computers called the binary number system. The hardware unit of a computer's memory is called the flip-flop, which holds the electrical energy. The basic unit of storage is called bit, which is basically represents the energy in its corresponding flip-flop. A flip-flop can have only 2 states, just like a bulb, that is on or off. Hence, we can have only 2 values, that is 1 or 0. Now, since this numbering system can hold only 2 values, we call the numbering system a binary or a base 2 numbering system. Now, how can we find the sequence of numbers using 0 and 1? How can we find the sequence of numbers using 0 and 1? Well, the first number can be 0 followed by the second number, that is 1. Next, watch. Well, we use the same concept we had used in the decimal number system. That is, consider resetting the value in the current position, that is the units position, and increase the value in the next position, that is the tens position. Since the last 2 numbers had 0 in their tens position, first or the tens position, now the same symbols in the zeroth position or the units position are being repeated once again. But the symbol in the tens position is incremented to 1. Thus, we get the next two numbers, that is 10 and 11. Next what? Again, a similar logic will be applied. So now what? Now that we have already got the four numbers, that is 0, 0, 0, 1, 1, 0, and 1, 1, we will now take a look at the values in the hundreds position. Since till now we didn't have any value in the hundreds position, we can consider that the value was 0. So in order to get the next four numbers, we will simply repeat the symbols in the units and the tens position of all these four numbers, and we will simply increase the value in the hundreds position or the second position from 0 to 1. Thus, we get the next four values, that is 100, 101, 110, and 111. Now, what is the value in the thousands position? It's again 0. Since we have written nothing, it means it's 0. So what we will do now, we will again repeat the values from units position to the hundreds position, that is from 0th position to the second position once again, and now we will change the value in the thousandth position to 1. Thereby, we get the numbers as given. The corresponding decimal numbers to them are also given in the blue color. Now that we have understood how the binary system works, let us see how we can convert a binary number 1100 to its decimal equivalent. The idea is very similar to the one that we had used earlier. The position values remain same. But since we are dealing with binary numbers, the base value will now become 2. Applying the same formula, that is finding the cumulative sum of the product of the symbols to each position and the base raised to the power of the positional weight, we get the decimal equivalent of 1100, which is 12. That means we multiply 1 to the value of 2 raised to the power of 3, and then add it to 1 multiplied by 2 to the power of 2, then add it to 0 multiplied by 2 to the power of 1, followed by 0 multiplied by 2 to the power of 0. After we add them all, the value that we get is 12, which is the decimal equivalent of the binary number 1100. Another way to find the decimal equivalent of a binary number is to simply list the values of the base raised to the positional weight from right to left. As 2 to the power of 0 is 1, the rightmost weight is listed as 1. Similarly, the next weight is 2 to the power of 1, which is equals to 2. The third weight, therefore, happens to be 2 to the power of 2, which is equals to 4, and so on and so forth. With increase in the position, the weight gets multiplied by 2 in each step. And accordingly, we have the weights as given in red. Now, if we simply add the weights corresponding to the symbols 1 of the binary number, we will get its decimal equivalent. As in this case, you can see the numbers, the symbols are 1 corresponding to the positional weights 512, 128, 32, 16, and 2. So we add up these positional weights to get the final decimal equivalent value, which is equal to 690. However, binary numbers are not always integral. In case they have symbols after the decimal point, they are treated as given in this particular slide. The decimal equivalent of the integral part, that is the part before the decimal point, is converted in the way that we just discussed a couple of slides earlier. But for the fractional part, however, the positional weights are listed in linearly decreasing order from left to right, starting with -1 as shown. Now, for finding the decimal equivalent of the fractional part, similar approach is used. That is, the cumulative sum of the product of the binary symbols after the decimal point and their corresponding positional weight is found and listed after the decimal point in the decimal number as shown. So here we multiply the 1 after the decimal point to 2 raised to the power of -1, then add it to 0 multiplied by 2 raised to the power of -2, and then add it to 1 multiplied by 2 raised to the power of -3, which gives us 0.5 plus 0 plus 0.125, resulting in the value of 0.625 base 10. So the integral part got converted to the decimal equivalent of 13 base 10, and the fractional part got converted to 0.625 base 10. So together, combining the two, we can see that 1101.101 base 2 is equivalent to 13.625 base 10. So with that, we come to the end of our today's tutorial. If you could follow my tutorial, please hit the like button and share it with your friends. Also subscribe my channel to get access to more such tutorials. Thank you.